Hi, Mr. Miscue. So this right here is my presentation on Big O, and Big O is how you measure efficiency in terms of coding. So first, let's start off with the question: what's the best way to sort an array? So I'll give a couple examples. Stooge sort, which sorts the first 2/3 and then the last 2/3. BOGO sort randomizes the array until it's sorted. That's my personal favorite. Bubble sort compares two elements until it's sorted. Selection finds the smallest, puts it in the front. Insertion, kind of like bubble, but as soon as it sorts pair, it goes back. Cocktail sort finds the largest and smallest, puts them at the extremes, and repeats for the elements in between. And redex sort, which is the one that I made, or rather coded myself, sorts the array by looking at the digits. So which one should we pick? Well, there are many methods of sorting an array. As you can see, this is a quick little screenshot from the Wikipedia page of short sorting mechanisms, and the list goes on for quite a while. Which one should we use? Well, here I have a quick table showing these different sorts. So you can see Stooge sort has best case scenario of O to the n to the power of 2.709, and the worst case is the same. BOGO sort, the best case is O to the n, worst case is unlimited. But let's think first, what is O? O is a way of measuring complexity and efficiency. How do we access elements of an array, and how do we access elements of a stack? So here's a little diagram of a stack compared to an array. So in an array, if you want to pick the perfect pancake, you look at one element, and since they're all laid out in front of you, you can pick that one. However, in a stack, if you want to pick one element, or in this case one pancake, and that pancake happens to be the bottom one, you have to go through all of the ones on top before you can reach it. So as you can see, the access efficiency of a stack is O to the n, because it clearly depends on how large the stack is, whereas an array is just O to the 1, because it doesn't matter how large the array is. If you want to access any element, it'll only take one line. So which one should we pick? So BOGO sort looks pretty good. Best case scenario is O to the n, but our worst case is unlimited. What about bubble sort? It's also O to the n, but the worst case is O(n squared, so not very good compared to some of the other ones. Selection is O(n squared for both times, so we can pretty much rule that one out. So there's a problem. If we know the array that we need to sort beforehand, we can pick the best algorithm. So for example, BOGO sort, it may work perfectly if the array happens, or if it randomizes it and gets it sorted the first time. However, most likely it's not going to get it right the first time. So the thing is, we don't know what our array is going to be beforehand, so we don't really know which sort to pick. So our solution is to look at the average between the two, the best and the worst case, but to keep it safe, I like to look closer to the worst case scenario. So in this case, our winner is going to be redex sort, because it has the best and the worst case scenario of O to the nk. And as you can see, if k is equal to n, then it's no better than bubble sort, for example. But luckily in most cases, k, which is the length of the integer, is less than n. So for example, if we had an array 4 numbers long, with the highest number being 9,999, so the array is 4 long and the highest int is 4 long, then it's just going to take as long as bubble sort. But an array 10 long will only take as long as bubble sort if the largest is 9,999,999,999. However, in that case, we run into an int overflow. So how do we calculate O? So for arrays, we're going to count how many times the for loops run, and for data structures, we count how long it takes to access an element. So let's start simple, an array. There are no loops, so regardless of whether we want to access the first element or the last one, it only takes one line. For a stack, our best case scenario is going to be O to the 1, because that's going to return the last element of the stack. If you go back to the pancake visualization, that's like taking the pancake at the top. But our worst case is O to the n. So here you can see the code segment that will get the last element of a stack. So basically, we're checking as long as the stack isn't empty, keep taking off elements and storing what they are. So this is the code, or the main code for my radix sort program. So we're going to calculate O for it. So as you can see, we have a for loop encapsulating everything else. So we're going to have to multiply that, multiply whatever's inside that for loop by however many times the big for loop runs. So in this case, you can see it runs max times, and in this case, max is how long the longest integer is. So we come to our first for loop. That's going to run nums.length times, which in this case we'll call it m. Come to our next for loop, which is going to run 9 times. I did 110.length, but 110 is always length 10, so you can see it's going to run 9, so n plus 9. We come to a next for loop, which is going to go through it however long the array is again, and to our final for loop, which is going to run through 10 times. So you can see our efficiency in this case is going to be O to the 19m plus 2nm, which is why my code was so inefficient, sorry. When I tested it using random data structures, bubble sort and sometimes even BOGO sort happened to work a lot faster than mine. However, in a better and more efficiently coded radix sort, the efficiency is going to be ONK. So let's look at bubble sort. So we can see that first we have a for loop encapsulating everything, that's going to run n times. And then second we have another for loop, and that's going to run n times as well. And so our final efficiency is O(n) squared. And keep in mind this is for the worst case scenario. So that's the end of the slideshow, but I think I'd also like to talk a bit about contest problems and applications, since that was a big part of this assignment. So in any situation in a contest problem where one of the issues is sorting an array, or perhaps choosing which data structure to use, this is a good scenario in which big O is going to come in handy, because you can find out which one's the most efficient. And clearly this is crucial if your contest problem has to do with efficiency.